Welcome back, everyone, to Security Weekly's Virtual Hacker Summer Camp. I believe this is the last micro interview in the series. It's been a really fun week. And if you want to hear about JavaScript security, I am fortunate to have with me Taemin Park, a fifth-year PhD student at the University of California, Irvine. Taemin, welcome.
Hi, everyone. Yeah, nice to meet you.
Yeah, it's nice to have you on the show, Taemin.
Yeah.
JavaScript is a weird animal and beast. I personally do not really like coding in JavaScript. I'll admit that. And what I learn about JavaScript is only so I can exploit stuff, not so I can actually build anything, right?
Yeah, me too, actually. Yeah. I don't use JavaScript for just writing code or something like that. I just want to see inside of the JavaScript engine and exploit it and do some hacking stuff.
Well, and I know this is kind of a broad topic in JavaScript security because JavaScript is in so many different places today. Which is why as attackers we have to have some level of understanding to exploit it, right? Building it, I think, it's a different thing. But it's in the browser, but there's various ways to interact with it within the browser. The DOM in the browser, web applications on the server side. Then you've got client side. You've got full-blown client applications with Node. It ends up everywhere, right? I guess what are some of the approaches to JavaScript? I guess start with the vulnerability side of it. Where did you find it to be most vulnerable to attack?
Yeah, actually, JavaScript can be anywhere in, like you said, the server side or client side. And mostly, I think the JavaScript in browser is, one of the things that attacker can exploit because think about it. What are you doing just right after turning on the computer? You might just run any browsers to searching for something in the internet. So everyone uses browsers right after turning on the computer, and the browser has JavaScript engine embedded, and the JavaScript engine itself could have vulnerability attacker can exploit. So if the attacker can exploit the JavaScript vulnerability, the impact is really, really huge. So I think this is kind of the client side of the JavaScript engine is something that I want to exploit, and the talks that I had on the Black Hat is also kind of related to this one. But this exploitation and vulnerabilities also can be used for kind of server side JavaScript engine too.
Sure. Yeah, but I agree. The browser is the most common way, and it's really kind of messed up if you think about it. You're just by visiting a website, you're executing the code that's coming from that website, right? But now there are certain protections inside the browser to limit how that code can be executed. Does some of your discovery kind of fall in the area of how you get outside of that?
Yeah, actually, this is kind of called the Sandbox Mechanism because JavaScript is running not on top of the CPU, but on top of the interpreter or script engine. And script engines will check whether the programmers can have some kind of mistake, like a typist check or the boundary misplacement and something like that. These kind of things are done by the script engine itself. So any mistake in writing code in JavaScript does not produce any vulnerabilities and any bugs at all. But the funny thing is that the JavaScript itself is written in JavaScript engine itself is written in unsafe languages such as C or C++. And the size of the JavaScript engine is getting bigger and bigger. And every week and every month, that bugs are reported for the JavaScript engine. So your code is fine. Your code does not have anything wrong. But if you run your code on the JavaScript engine, and if there is a vulnerability inside of JavaScript engine, you cannot avoid this kind of hacking or this kind of vulnerability exploitation. That's why the JavaScript engine protection is really important.
I see. I can write really well. I can't, but let's just say I could write really good JavaScript code that followed all the standards and best practices and was very resilient. But that resiliency relies upon the resiliency and integrity of the engine that is included inside of the browser in this particular case, right?
Right. The engine itself, the engine itself check whether programmer has a mistake, but engine can have the vulnerability itself. So it's kind of the funny that we can. So I cannot say that JavaScript is kind of type safe or memory safe because engine itself is not that type safe and memory safe at all.
Right. Is it what are the JavaScript engines that are built into popular browsers? Do they kind of mix and match, or is it all pretty standard? Does Google in Chrome maintain an open source JavaScript engine that's specific to Chrome?
Yeah, Google maintains the V8 and Safari also has kind of WebKit, and they have their own version of the JavaScript engines. They are just updating, and also Firefox has SpiderMonkey, which is also another JavaScript engine, and their implementations are totally different. I looked at all of the codes and I see that they choose a different approach, how to implement the JIT compiler, how to implement interpreter. So it's very diverse, and then you see that it means that attacker can choose whatever the engines they like to exploit. And if there's a kind of bug in V8, they can just choose to use the V8 to exploit. And if there's kind of the bugs found in Firefox or something like that, they can just choose that browser. So yeah.
Now, does the browser kind of separate the JavaScript engine in its own sandbox, or is the browser itself doing the kind of sandboxing? Like, how does that sandboxing work? Is it all just kind of lumped into one in the browser, or are there different sandboxes for JavaScript engines running and things like that?
So basically, JavaScript itself has a language level sandbox. So if you have to write a code, and let's say you can make a buffer, and you try to access some out of bound of the buffer, and then the JavaScript engine itself has an interpreter, and when interpreter try to execute that code, and that check the property of the index and the size of the buffer, and then if the index is out of the bound of the buffer, it just disallows the further execution. So JavaScript itself has the sandbox, and
Gotcha.
And of course the browser also can have some kind of security mechanisms. They can just protect from the attackers to exploit, or the DOM or other engine components. But the JavaScript itself also has it has the sandboxes.
I got you. So the DOM in the browser using JavaScript is also using the interpreter as well and working in conjunction with each other.
Yeah.
That's really it's amazing to unravel this technology, because it's not something I delve that deep into all the time. When I do, I'm always like, this is just, it's amazing how, because I think a lot of us take for granted like how the browser works, and we attack web applications, and we've got some client side attacks that are basically tricks in JavaScript. But what are some of the specific techniques? Do they go across browsers, or like what are some of the an example of a specific technique to exploit the JavaScript engine?
The basic exploitation. So it's been more than 10 years, and one of the famous exploitation technique is just spraying. Actually, the attacker wants to run his code inside the victim's machine. So in order to do that, the attacker can just inject or reuse the code inside of the machine code. But in the JavaScript case, the attacker can encode his malicious code inside of the constant in the JavaScript, and then use the vulnerability to make the program counter jump in the middle of the constant and where attacker's code reside. This is kind of really good.
Yeah, the most common one is like a heap spray attack, right? It's using JavaScript that's interpreted by the engine to heap spray memory, right?
Yeah, this is just spraying and heap spraying and something like that. Or the other techniques are kind of using race condition. So that the JavaScript support multi-threading capability, and then when JavaScript running some code, sometimes they just convert this kind to some portion of the code into machine code so that it can be directly executed by the CPU.
Mm-hmm.
So, but generating machine code means that the code should be, at some point, it should be writable, right? And then JavaScript to write the code onto the memory and make that area read only and execute.
Mm-hmm.
But attacker can spawn a new thread, and when they are just generating machine code, the new thread is still the CPU cycle and overwrite attacker's code on top of the just generated code. Yeah, right. This is kind of using race condition to overwrite the machine code.
Gotcha. In that interpretation into machine code, are there also kind of like serialization attacks that present themselves as well?
You mean serialization attacks?
Serialization attacks, yeah.
I don't know about the serialization. What is the specific things about the serialization attack?
It's more kind of tricking the JavaScript engine to run different machine code, basically.
Different machine code. So that could be either just injecting or just reusing the code. But the serializing, you mean just chaining some existing machine code together?
Inside your code so that it gets executed without knowing it.
Mm-hmm. Yeah. Right.
That's also an attack vector. That's interesting.
That's true. Yeah. And also, G-Spring is really just strong. Some kind of countermeasure have been developed, which is kind of constant blinding, which means that when attacker tries to encode his code inside the constant, and our defense side, we just encode the constant for every usage. So when just emit out the constant, we just encode with some secret value and just emit out that constant so that attacker cannot use that constant anymore. And whenever that constant is used, our engines use a secret key to just decode that constant for
so you can detect if it's changed, basically, right?
Right.
Mm-hmm. Gotcha. Did you study the engines that are in the three different major browsers? And are there like very big differences in the exploitation techniques between Safari and Chrome and Firefox? Yeah,
actually, I have just studied Safari, but mostly SpiderMonkey, and I try to my attack is some kind of a little bit different from the race condition attack or G-Spring attack, and my attack is corrupting actually the bytecode. Bytecode is also kind of the intermediate representation executed by the interpreter. And then, so that I looked at the interpreter mechanisms in SpiderMonkey and V8 and Safari, whatever. And then I found that the SpiderMonkey is much easier to develop some exploit because the interpreter itself is written in C language. But for example, in Safari case, their interpreter is like written in some really complicated, almost like the machine language, like some low-level languages. So it's not that easy for me to just develop some exploit. And Google Chrome also, they have kind of some complicated mechanisms in interpreting the bytecode. And this kind of, they use some kind of indirect or direct threading for interpreting. But the SpiderMonkey case, it just interpret every bytecode using some simple switch statement. So it's much more easier to exploit.
Other recommendations you have to protect the JavaScript interpreters and make them more resilient and resistant to attacks?
So this is kind of related to the defense that I developed. The defense is that I just minimize the permission of the import the data as small as possible. So I found that the import data in the interpreter is JavaScript bytecode, object table, and JavaScript object and JIT code. And currently they are writable or readable, and the permission is really open to be corrupted. So the defense that I develop is that I make those object some kind of import data and make it readable so that attacker cannot manipulate it because it is not writable. And in the G code case, G code is basically readable and executable, but my defense take the readable permission away and then make the cheat code executable so that attacker cannot read and learn about the gadgets they can just exploit.
Right. Gotcha. That's awesome. And have you given your talk at Black Hat already?
Yeah, I already gave. And then this is, the things that I just discussed before is related to my talk.
Gotcha. And do you have a Git repository with some example code and things like that?
Yeah, actually, my defense and attack is in the GitHub of our school's account, our group's account, and our group's account is private. And I try to polish all the codes. And then if I get a permission from my advisor and schools, I can just make it public so that other people can use my defense or test my exploit.
That's awesome. Yeah, if you do release it, we'd send us a note, and we'll make sure we talk about it on the show and direct people to go review and test the research. It's awesome. Well, Taemin, thank you so much for appearing on Security Weekly. Yeah,
thank you so much. It was really nice. Yeah, really good chance for me to have an interview. This is actually my first time to having an interview in the broadcast and live stream.
Oh, awesome.
Other than the conference.
Well, you did great. Thanks for sharing your research with our audience. That will conclude the interview for today. Stay tuned. Is there more? I don't think there's more interview. Just a show. This is the last one. PSW, Paul Security Weekly, 7 p.m. Eastern tonight. Stay tuned.